Welcome to part 1 of my video playlist about the best methods to convert aliphatic alcohols into alkyl bromides. This is an important transformation because alcohols are readily available but can usually not be used as alkylating reagents. Alkyl bromides, however, are powerful electrophilic alkylating reagents capable of alkylating many different compounds, such as amines, thiols, alcohols, aromatics, and deprotonated CH acidic compounds. This first presentation is about hydrogen bromide as deoxybrominating reagent. In the second part, the use of reagents containing phosphorus-bromine bonds and some other more exotic reagents will be discussed. Alkyl bromides are strong alkylating reagents and react about 40 to 80 times faster than the corresponding chlorides, as shown here by the relative rate of the quaternization of quinoclidine in chloroform. Therefore, many alkyl bromides show a high acute toxicity and mutagenicity. Even most aryl bromides are hepatotoxic, and only few drugs with brominated arenes or heteroarenes have been approved. Alkyl bromides are more expensive than alkyl chlorides, but for many reactions alkyl chlorides are too unreactive and cannot be used. Depending on the reactivity of the alcohol and on the solvent chosen, deoxybromination by HBr can proceed by carbocation formation or by an SN2 type displacement of a protonated hydroxyl group. In addition to carbocation rearrangements, typical side reactions include the formation of ethers or of olefins by elimination. Olefins can also be converted into alkyl bromides by treatment with HBr, but bromide usually adds to the more stable secondary or tertiary carbocation, and primary alkyl bromides can therefore not be prepared from terminal olefins. Only terminal electron-deficient alkenes will add bromide at the methylene group and yield primary alkyl bromides. HBr is a significantly stronger acid than HCl, what causes not only an increased corrosiveness, but also a higher tendency to form carbocations from alcohols or other organic compounds. Carbocation formation is also one of the reasons why deoxybrominations with HBr do not always proceed with clean inversion of configuration, but often yield mixtures of stereoisomers. Solvents must of course be acid resistant, and acetic acid, water or sulfuric acid are mostly used for this reaction. Ether and olefin formation can often be suppressed by increasing the concentration of bromide ions in the reaction mixture, and quaternary ammonium bromides or zinc bromide have therefore been used as additives to enhance the rate and yield. Strong acids such as sulfuric or phosphoric acid can also be used to further increase the reaction rate. Sulfuric acid, however, is slightly oxidizing and tends to generate bromine from HBr. Hydrogen bromide can be purchased as solution in water or acetic acid and is usually prepared by reduction of bromine. As an alternative to the use of pure HBr, it can also be generated in the reaction mixture from alkali bromides and phosphoric or sulfuric acid. One simple procedure for preparing alkyl bromides from alcohols is to heat a mixture of the alcohol, potassium bromide and sulfuric acid to reflux. If one's starting alcohol contains electron-rich arenes, however, phosphoric acid may be a better choice because sulfuric acid will oxidize HBr to bromine and cause the bromination or sulfonation of the arene. Phosphoric acid is not acidic enough to protonate bromide stoichiometrically and will usually only generate a low stationary concentration of HBr. Phosphoric acid will, however, also activate alcohols towards substitution by protonation at oxygen. Another way to generate HBr is to reduce bromine, for instance with hydrogen, phosphorous acid, hydrogen sulfide, sulfur dioxide or with sulfur, as in the example shown here. This is one of those examples where HBr was generated from potassium bromide with sulfuric acid. Despite the strongly acidic reaction conditions, no secondary butyl bromide was obtained as byproduct. The risk of isomerizations during such reactions can sometimes be further decreased by constantly removing the product from the reaction mixture by distillation. In this example, one of the two hydroxyl groups of diethyl tartrate was displaced by bromide with inversion of configuration. The final free alcohol was obtained by HCl-catalyzed transesterification. Despite the excess of HBr, only one hydroxyl group was replaced, probably because only the cyclic deoxolenium cation was electrophilic enough to react with bromide. This cyclic deoxolenium cation was formed by esterification of one hydroxyl group followed by cyclocondensation with the second hydroxyl group, not by substitution. Therefore, only one SN2 reaction occurred at the bromine-carrying carbon atom to give a clean inversion of configuration. From the intermediate bromoacetate, no cationic precursor for the dibromide could be formed, and therefore the reaction stopped after one single deoxybromination. This example is similar to the previous one in that the reactive intermediate was probably a dioxolenium cation. The regioselectivity of the ring opening of these intermediates is, however, difficult to predict. In this case, steric accessibility was the decisive factor, and not carbocation stability. This suggests that no free carbocations were formed as intermediates, but only the dioxolenium cation. Carbocation formation is probably inhibited by the electron withdrawing effect through sigma bonds by the other oxygen atom. In this example, depending on the amount of HBr and on the reaction temperature, the starting diol yielded two different products. Because substitution at neopentylic positions is slow, the first step in these reactions was probably the acid-catalyzed hydrolysis of the ester groups, followed by decarboxylation. A large excess of HBr and a high reaction temperature led to the substitution of both hydroxyl groups by bromide. At lower temperature and with a smaller excess of HBr, only one hydroxyl group was substituted while the other underwent elimination. Ethers can be cleaved by strong acids, and treatment of methoxyethanol with HBr did not yield the corresponding bromide but a mixture of products instead. Among various strategies tested, only conversion into a sulfonic acid ester followed by displacement with bromide gave good yields of 2-methoxyethyl bromide. A more convenient strategy was the conversion into a chlorosulfinate by treatment with thionyl chloride, followed by conversion into a bromosulfinate by treatment with HBr and thermal desulfonylation. A similar strategy would have been to use thionyl bromide instead of thionyl chloride, but thionyl bromide is not as readily available and stable as thionyl chloride. Unfortunately, HBr can cause a number of unexpected side reactions. Because HBr is such a strong acid, it readily adds to alkenes, as during the deoxybromination of allyl alcohol shown here. HBr can also add to alkynes, sometimes under surprisingly mild reaction conditions. In this example, addition to the alkyne was faster than deoxybromination of a secondary propargylic alcohol. Even electron-deficient alkenes can react with HBr. Methyl acrylate, for instance, did not polymerize but cleanly added HBr at room temperature. Only a small fraction of the ester was demethylated to the acid. In this example, HBr added to the double bond of acrolein and simultaneously catalyzed its acetalization. Because of its high acidity and nucleophilicity, HBr can also be used to cleave ethers. Not only methyl or benzylic ethers, but even less reactive ethers, such as tetrahydropyrene. In this example, an aqueous solution of HBr was prepared by reducing bromine with sulfur dioxide. A large number of other functional groups can be cleaved or hydrolyzed by HBr. These include epoxides, acetals, esters, amides, nitriles, carbamates, alkyl arenes, and triaryl methanes. In the example on this slide, a nitrile was hydrolyzed completely during a deoxybromination with aqueous HBr. Other potential side reactions include the elimination of hydroxyl or other functional groups and the typical rearrangements of carbocations. Then, if the concentration of bromide ions is too low, ethers or products of aromatic cyclodehydration may be formed. Instead of undergoing elimination, other potential leaving groups, such as other halides, sulfonates, alkoxides or carboxylates, may also be displaced by bromide. bromide can easily be oxidized to bromine radicals or elemental bromine, for instance by peroxides, sulfuric acid, air, or DMSO. This in turn can cause the oxidative bromination of a large number of functional groups. Finally, the bromination of ketones is reversible, and under suitable conditions, alpha-bromoketones can be debrominated by HBr. Here's a short selection of some further examples. Despite its corrosiveness and the many potential side reactions, deoxybrominations of alcohols by hydrogen bromide are an important way to prepare alkyl bromides. Also because for deoxybrominations there are fewer reagents available than for deoxychlorinations. The brominated analogues of thionyl chloride and phosgene are not readily accessible, and the only additional generally applicable reagents for deoxybrominations are phosphorus bromides, which are discussed in the next presentation of this playlist.